Hello students, welcome to electronics class, and today we will start off with the second chapter. First chapter was all about introduction to electronics. I hope you have understood and you have learned those abbreviations and inventions and also applications of electronics in various fields. So today we will see principles of electricity, network theorems, and AC principles. We are not going to start off all of them. Today we are going to only start with the principles of electricity. Certain topics you must have already heard, you have learnt also, but for electronics you need to know in detail. So we will take up one at a time. So basically what we are doing today is we will be discussing what is charge, properties of charge, and we'll define what is current and what is potential difference, and then we will see Ohm's law statement, and from there we will get what is resistance, and then we will put resistors in series, resistors in parallel, and resistors, combination of resistors, series parallel combination. This much we are going to discuss today. Okay, so first of all, how did the name electricity come into being? This word electricity originated from a Greek word electron, and this was coined by Dr. William Gilbert, an English scientist and a physician. Okay, this dates back in 1600s. It is from since then we have been using the word electricity. So even before knowing what is electricity, let us see certain experiments. When you take silk cloth and rub it on glass rod, okay, and you take one more silk cloth and rub it on glass rod, and if you bring glass rods together, it was seen they are repelling each other, or if you bring silk cloths together, they were repelling each other. Then they figured out that the glass rod is having what is known as positive charges and the silk cloth is having negative charges. Similarly, they did the experiment on ebonite rod and animal fur. When they rubbed ebonite rod with animal fur, it was eventually found that ebonite rod is negatively charged, whereas animal fur is positively charged. How did they come to know? They brought ebonite rod and glass rod near each other. They attracted, and silk cloth and animal fur were attracted after they were rubbed. So they figured out that there must be two types of charges, and the same type of charges repel and different types will attract. That was the conclusion. Okay, so this kind of force is called electric force. So this is the property of certain materials which exhibit this kind of force. So what is charge? Charge is property of certain particles which is responsible for electric force. So materials can be charged by various means. One is by friction, which we saw just now, which we discussed just now, or by conduction, induction, electric field, and heating. This another experiment you must have already seen. When in the winter, when you comb your hair and when you bring it close to pieces of paper, the comb starts attracting them. So that is also another example for electrostatic force. Okay, so keeping this in mind, let us see the properties of charges. Properties of charges, as I told you, like charges repel, unlike charges attract. There are two types of charges, positive and negative. Charges are conserved, means they follow conservation of energy, means charges can neither be created nor destroyed. Charges reside only on the outer surface of the charged conductor. Charges is not affected by motion. If you move, it doesn't lose or anything. Charge is quantized, means it will always appear in whole number. Okay, like 20 or 45, like that, not 20.5, not 45.25, no, not in fractions, always in whole numbers. Magnitude of charge on one electron or proton is 1.602 into 10 to the power of minus 19 coulomb. You have to remember this number. At least you have to remember 1.6 into 10 to the power of minus 19 coulomb, because we are going to use this for many problems. Magnitude of charge on one electron is equal to 1.6 into 10 to the power of minus 19 coulomb. If n electrons pass through a cross section of conductor in time t, then total charge passed is n times E, where E is the magnitude of charge. Okay, magnitude of electron or proton, which is 1.6 into 10 to the power minus 19 coulomb. Coulomb is the unit of charge and it is represented as capital C. Okay, so SI unit of charge is coulomb. Next, if a charge on single electron is 1.6 into 10 to the power of minus 19 coulomb, then how many electrons are present in 1 coulomb? For that, all you have to do is 1 divided by 1.6 into 10 to the power of minus 19. If you calculate this, you will get charge on 1 coulomb is nothing but charge on 6.25 into 10 to the power of 18 electrons. What does this mean? 1 coulomb of charge has so many electrons. Can you imagine that? It's huge. That is why 1 coulomb is a huge quantity. We don't use 1 coulomb for all the problems. We will have 1 microcoulomb, 1 millicoulomb, like that. Milli means 10 to the power of minus 3, micro means 10 to the power of minus 6. Okay. So, next we will define what is electric current. We are defining few terminologies before even starting off with electronics, okay, pure electronics. So, all these terminologies are important. What is electric current? Rate of flow of charge in a conductor is known as electric current. So, current is defined as charge divided by time. Rate of flow of charge. Charge by time is current. Current is always represented by I. Charge is always represented by Q. Time is as small t. So, Q is nothing but number of electrons passing through that particular conductor, and E is the magnitude of charge, 1.6 into 10 to the power of minus 19. This will tell us how much of charge divided by T. Okay, this defines current. That is what I told you just now, is it is given here, and SI unit of current is ampere. You must have heard of, if you in your homes you have 5 amps if it is all electric home, 5 amp of current will be flowing. Maximum current can be 5 amps, or in your devices also it will be written it can withstand only 12 milliamps, things like that. So amps or ampere is the unit of current. Now, if small amount of charge, if we are talking about dq, and in small time dt, then the current, small current I can be given by dq by dt. When we are talking about small variation in current, then we will have to represent it by small I. If it is a fixed charge, fixed time, then it will be fixed current, as we discussed here. Capital I is for fixed current, fixed charge, fixed time. This is for varying charge, varying time, varying current. I is also equal to dq by dt. So, how to define 1 ampere? The unit of electric current is said to be 1 ampere if 1 coulomb of charge flows through cross section of conductor in 1 second. So, we have I is equal to q by t. If this is 1 coulomb and this is 1 second, then we say I is equal to 1 ampere. So, how to say 1 ampere of current? It is when 1 coulomb of charge flows through cross section of a conductor in 1 second. Then we say current flowing in the conductor is 1 ampere. Okay. So, if this is the conductor, this is the battery, and the battery is supplying electrons, then the electrons flow from negative to positive in this direction. Electrons flow in this direction. But then direction of current is always considered opposite to the flow of electrons. See, direction of current is opposite to the flow of electrons always. So when you have to indicate from positive to negative, you should remember this. You're not indicating negative to positive. Even though flow of electrons constitute current, we always have to represent positive to negative. That is the direction of current. Like I told you, 1 ampere is a huge quantity. We use 1 milliamp. That is, in small m we use for milli, which is equal to 10 to the power of minus 3, or 1 micro here. is 10 to the power of minus 6. Micro is represented like this. Or 1 nano means 10 to the power of minus 9 and it is represented as small n. And 1 pico means 10 to the power of minus 12 or small p. Normally these two milli and microamps are used, nano and pico, just you should for your information have given. For all problems we'll use milli and micro. Okay, now let us define what is potential difference or voltage. That what is the power supply that is supplied to your houses, what is the voltage? 230 volts, remember. So this potential difference is nothing but voltage. So how to define potential difference? Potential difference between 2 points is the work done in moving unit charge from one point to another. So potential difference is given as work done divided by charges transferred. Or potential difference V, it is always represented as V is equal to W, which is work done, divided by Q, that is the charge. V is equal to W by Q. These equations are important. I is equal to Q by T, V is equal to W by Q. These equations are important. W is the work done, Q is the charge. SI unit of potential difference is nothing but volt. Okay, 230 volts, remember. So volt is the SI unit of potential difference. How to define 1 volt? Here when I come back to the equation, V is equal to W by Q. 1 volt is equal to 1 joule of work done divided by 1 coulomb of charge. How to define 1 volt then? It is 1 joule of work done in moving 1 coulomb of charge from one point to another is known as 1 volt of potential difference. That is what is defined here. The potential difference between 2 points is said to be 1 volt if 1 joule of work done in moving 1 coulomb of charge from one point to another, or 1 volt is equal to 1 joule by 1 coulomb. Like I told you, potential difference and voltage mean the same. Okay, next we have to know what is direct current or DC current or voltage and AC current or voltage. DC means when voltage or current is constant with respect to time. That is known as direct current. So that is normally a battery, your AA battery, ever ready batteries are there. We connect it, right, for watches, for clocks. Even your watch will have a battery. They're all DC voltages. DC power supply it is. So it'll here the current flows only in one direction, positive to negative, positive to negative. It goes like this, and it is shown in one direction only, and the bulb will glow. Alternating current means when the current is flowing in both directions, positive, negative, it goes on alternating periodically. That is known as alternating current. It has positive cycle also, negative cycle, positive, negative, it goes on repeating, and this is the time period from beginning to ending of one cycle. Okay, so alternating current is represented like this. This is a sinusoidal symbol. So here when the current is flowing, it once flows in this direction and next it flows in the opposite direction, like this, like this, like that. That is alternating current or AC current, AC voltage. The power supply that you get from KEB is alternating current, AC, 230 volts AC. For cell phones and all, after charger, what it gets is DC, 12 volts DC. Your battery is DC. Okay, let us see the difference between the two. This is the symbol for DC. This is the symbol for AC. Like I told you, it remains DC remains constant with respect to time, whereas AC varies alternatively with respect to time, periodically with respect to time. DC has no frequency, zero frequency, whereas AC has certain frequency. That is why 230 volts power supply, 50 hertz frequency we say. Okay, and all these your FM station frequencies are all AC. If it is 94.3 FM, 93.5 FM, whatever your favorite channels are, 101.3 megahertz, they are all megahertz frequency, they are all AC. Okay, DC has no frequency. While transmitting DC, there is maximum energy loss. That is why while transmitting AC, there is minimum energy loss. That's why we are having AC at home transmitted. DC is not transmitted. Through the transformers we are getting AC, right? So because minimum energy loss will be there while transmitting. That is the reason AC is transmitted. Current flows only in one direction and it is represented as capital I, capital V, DC. Whereas AC it is represented as small I and small v, because it keeps changing and it varies at every instant of time. It is called instantaneous alternating current and voltage. It at every instant of time the current and voltages are different. It varies. That is why they are represented by small I and small v. Here it is capital I and capital V. Examples for DC are cells, batteries, regulated power supply, DC generators, and these are the sources of DC. AC generators, oscillators, function generators are all examples of AC. Okay, learn these, it's very important. If you learn, then you'll appreciate when we talk about these later. Next we'll talk about Ohm's law statement. Ohm's law is a very basic law and we use it everywhere in electronics. Every single place you have to use Ohm's law. So you have to learn this thoroughly. What is the statement? It states that current flowing through the conductor is directly proportional to the potential difference across its ends, provided temperature and other physical conditions remain constant. So if this is the conductor with having a resistance R, and if this is the voltage or the potential difference applied across it, then if this is the current flowing through it, according to Ohm's law, current flowing through the conductor is directly proportional to voltage applied across it or potential difference applied across it. So what we say is I is directly proportional to V, or V is equal to I into R, where we have to have a proportionality constant, right? So V is equal to I into R, where R is the constant of proportionality known as resistance of the conductor. So the resistance of the conductor means it opposes the flow of current. So resistance is the property of conductor that opposes the flow of current flowing through it. More resistance means more it opposes. That's what you're supposed to understand. It is like having humps on the road. If you have big humps, will the speed be fast or slow? Like that. If the resistance value is more, current is going to reduce. Okay, and the unit of resistance is ohm, because Ohm's law, he is the one who gave us the relation between current and voltage, saying that V is equal to I into R. So resistance unit is ohm after his name, and the symbol is like this, omega. You have to practice this. This drawing is important. These equations are important. The statement is very, very important. Always it will be asked in tests and exams. Okay, so learn this equation. V is equal to I into R. Now symbol of resistor is like this. You have to draw pointed edges only. Practice this. And resistor is always represented as R, capital R. So V is equal to I into R is Ohm's law. By transposing, we can also write I is equal to V by R. Again, for R we can write it as V by I. So these are extensively used in all the problems. Next class we are going to take many problems, so you should know this. So this can be easily memorized by remembering this triangle. You write V here and I here, R here. So V is equal to I into R, I is equal to V by R is equal to V by I. All the three equations can be easily memorized by this triangle. Practice this. When you plot a graph, for Ohm's law we can plot a graph. In the lab you are going to do this experiment when you come. When you plot I versus V, okay, for a resistor you get a linear graph like this. So this is the characteristics of a conductor. When you keep varying the voltage across it, then the current also varies linearly. Next, there are certain limitations of Ohm's law. In the definition, in the statement of Ohm's law itself, he says that only under constant physical conditions and temperature remaining constant, isn't it? So what are the limitations? It's not applicable when physical conditions of a conductor are subjected to change. You cannot have anywhere and everywhere. He also says that it is not applicable for low and high temperature, and it is not applicable for non-linear devices such as electron tubes, semiconductors, discharge tubes, electrolytes, and it is not applicable for arcing devices. All these are the restrictions for Ohm's law. Ohm's law is applicable only for conductors, metals. So when it is applicable for resistors, metals, conductors, then we say those devices are ohmic devices. And for diodes, transistors, SCRs and all, it doesn't apply. Then those devices are called as non-ohmic devices. Simple as that. Whichever follows Ohm's law are ohmic devices, which do not follow Ohm's law are called non-ohmic devices. Next we'll see what are combination of resistors. Just now we defined resistor as the opposition offered by the resistor to the flow of current. Okay, so resistors are used extensively. You must have seen this kind. This is a resistor practically available in the market. This is another resistor. You also will know how to find the value of the resistor by seeing the color code later. In the lab, when you do the experiment, first thing I'll be doing is giving you resistors to find the color code. Okay, so we have to know combination of resistors. If you have seen motherboard or any board, circuit boards, PCBs, you would have seen so many resistors connected in series or parallel. You know, they're also soldered. All colorful things are soldered everywhere. So they can be either in series connection or parallel connection. So when they are connected in series, what is going to be the total resistance from one end to the other end? Or when they are connected in parallel, how do we know the total resistance? We need to derive the equations. Okay, so this series combination of resistors, this derivation is asked for 3 marks in the final examination. So you should know this. Okay, so we will see first series combination of resistors. When you have two resistors like this, when you connect next to each other like this, it is called series connection. So this is represented like this. Resistor, when you draw, you show like this. Another resistor is shown like this. So they are connected next to each other. This is series combination, and we call it as R1 and R2, and that is connected to the battery V, and the main current I flows through it. In series combination, same current flows through both the resistors. That is a speciality of series combination. Current is the same, but see the voltages? Voltage gets divided. The main voltage gets divided between the resistors depending on the value. If the value of the resistor is more, voltage drop is going to be more. If the value of the resistor is less, voltage drop will be less. So it depends on the value of resistance. So V1 across R1, V2 across R2. Now these two can be represented by single resistance. That is what we are trying to figure out. It is called RS, series resistance or effective resistance. And the voltage is represented, potential difference is represented as it is. So how to derive the expression for this? Now the total voltage we know is equal to V1 plus V2. Total voltage is what is divided, right? So voltage is equal to V1 plus V2. That is our first equation. By Ohm's law, by now you know Ohm's law. Ohm's law, what does it say? V is equal to I into R. So current I is flowing through resistor R1 and resistor is R1. I into R1 becomes V1. Same current flows through resistor R2. So I into R2 is equal to V2. That is what is our third and fourth equation. And the second equation is from this diagram. You have one voltage, one current, one resistor. So Ohm's law says that V is equal to I into RS. That is our second equation. Okay. What is the main equation? V is equal to V1 plus V2. So we have for V, for V1 and also for V2. Can we substitute all these here? When we substitute, we get I into RS is equal to I into R1 plus I into R2. I into RS is equal to I into R1 plus I into R2. I is common. Here also I is there. If you cancel out all i's, what are you left with? Rs is equal to R1 plus R2. So what is the conclusion here? When two resistors are connected like this in series or like this, symbolically we show like this, what is the total resistance going to be? It is nothing but sum of two resistors. For example, if you have 1 kilo ohm and 2 kilo ohm resistors in series, the total resistance is going to be 1 plus 2, 3 kilo ohm. Or if you have 100 ohms resistor here, 500 ohms resistor connected in series, what will be the total resistance? 600 ohms. Simple as that. You just have to add them. Okay, if there are many resistors, you can put R1, R2, R3, R4, many of them in series, similar to this, so many resistors in series, then total resistance, all you have to do is sum them up. Okay, so when the resistors are connected in series, you add them all, so total resistance increases when they are in series, remember that. Next we'll see when they are connected in parallel. When they are connected in parallel, it looks like this. So the two ends are joined here like this, two ends are joined here. These are the two resistors, real resistors. This is how they look. When you hold them in the lab, when I give you, they look like this. So when you connect the two ends here, and then connect it to the power supply like this, then this is called parallel combination of resistors. So here what happens, voltage across each of them remains the same, but the current gets divided. Main current coming from the power supply gets divided into I1, I2. So total current is nothing but I is equal to I1 plus I2, but the voltage across R1 is also V, voltage across R2 is also V. Now our job is to find what is the total resistance when they are connected in parallel. So if we call that as RP, which is a parallel equivalent resistance or effective resistance, then this can be replaced by one single resistance RP and the voltage supply as it is. So we have to find the equation for RP. Now again, at this point A, current divides, I told you, into I1 and I2. So we can write I is equal to I1 plus I2. That will be our first equation. By Ohm's law, remember the triangle, to memorize the Ohm's law I showed, current I is nothing but V by R. So from this equivalent circuit, we can write I is equal to V by RP. One resistor is there, one voltage is there, one current is there. So I is equal to V by RP. That is our second equation. Going back to the parallel combination circuit, we have two resistors and the current flowing through this is I1, resistor is R1, voltage I told you is V. It remains same for both. So what is the equation for I1 according to Ohm's law? I1 is equal to V divided by R1. That is our third equation. Similarly, I2 is equal to V divided by R2. That is our fourth equation. Now I we have, I1 we have, I2 we have. Can we substitute all these in the first equation? Then what happens? V by Rp is equal to V by R1 plus V by R2. All V's are here also, V is here also. We can cancel them out and we can write it as 1 by Rp is equal to 1 by R1 plus 1 by R2, or in this format, 1 by Rp is the total resistance equal to 1 by R1 plus 1 by R2. So when they are in parallel, it is reciprocal addition you have to do. Okay, now you can take LCM here, R1, R2, then R2 goes up, R1 comes here, then for RP what can we write? It's equal to R1, R2 divided by R1 plus R2. When two resistors are in parallel, it's equal to R1, R2 by R1 plus R2. I want you to remember this equation thoroughly. When resistors are in series, you add them. But when resistors are in parallel, it is reciprocal addition we have to do. But I want you to remember two resistors in parallel. Then we can go on with the 3, 4 and all that. First you remember this, when two resistors are in parallel, it is R1 R2 by R1 plus R2. Product divided by sum of two resistors will give you equivalent resistance of resistors in parallel. Now we can also have n resistors in series. Then all you have to do is add them all. You can have n resistors in parallel. All you have to do is take reciprocals and add them all. If all of these are same, 1 by R plus 1 by R plus 1 by R plus 1 by R, what is it going to be? It will be n by R. So, but 1 by Rp is n by R. What is Rp? R by n. That is what it is going to be. If there are two resistors in parallel, then you will be writing R by 2. If there are three of them, R by 3. If all the resistors are same, I'm saying if they are different, you have to use this only. If there are all same resistors in series, then it is going to be n times R. Same resistors. Okay, so we'll take problems and then solve. You can also have combination of resistors and resistors in series and parallel like this. These two are in series, these two are in parallel, again this is in series. So essentially R1, R2, R5 are in series, whereas R3 and R4 are in parallel. So how to write the final expression for resistance from A to D? It is R1 plus R2 plus R5 plus R3 R4 divided by R3 plus R4. Remember, when two resistors are in parallel, what do we do? R3 R4 divided by R3 plus R4. So you can take first parallel combination. Effective resistance between B and C means R3 in parallel with R4. This symbol means parallel. Okay, which is R3 R4 divided by R3 plus R4, and total resistance can be given by R1 plus R2 plus R3 R4 by R3 plus R4 plus R5. This is our equivalent resistance. We'll take up problems, some simple ones and then complicated, then you will get to know how to solve them. We'll solve problems based on Ohm's law and resistors in series and parallel in the next class. Okay, so let me end the session with this thought. We have to have good attitude, students, all of us. So what are all the good attitude? This is an attitude tree with all these parameters. In the sense, you should know how to appreciate, you should be committed, you should be creative, you should be enthusiastic, you should know what is independent thinking. Basically, you should know how to cooperate with each other. You should have integrity, very important. You should respect each other, you should tolerate others, and you should be curious to know new things. You should be empathetical, and you should be confident. Ultimately, only if you have confidence, you can achieve anything you want. Okay, go through the definitions that is given there. I found it interesting, I thought I'll share it with you. Okay, let me end the session. All of you, please go through, answer the assignment. If you have any doubts, now that you know my mobile number, you can WhatsApp and ask me also. I'll appreciate that. Assignment you can send it through my WhatsApp also. My WhatsApp number, I'll be able to see your assignment. Okay, I'll see you in the next session. Take care. Bye bye. Thank you.